So hello everyone and welcome to today's session. So now my colleague Alexander is joining.
So can you hear me, Jurlind?
Yes. Well, so it's more than punctual, so it's good to have you here, even though you had some technical issues, because usually you are more than punctual when it comes to appointments. So let's start together today, and today we have a topic about securing the layer below Kubernetes, and what we want to talk about is with respect to polymorphing as a technique for securing Linux operating systems. And this is where actually what we mean with securing the layer below Kubernetes. The agenda for today, as we have done all of these sessions and in previously, we do a very short recap of what we discussed the last time, and then we will continue with focusing with the topic of today, introducing operating system security, and especially focusing on the Linux operating system. So let us continue with what we did last time. I will just wrap up very short, and maybe Alex want to say one or two more things about it, as he is the expert matter in here, and you can always reach him out and learn from him about that. It's going to be fun. So KubeBuilder, what we learned last time, that KubeBuilder is kind of framework, a tool that you can use to build Kubernetes APIs by using CRDs, and it provides you a lot of, let's say, help and tools. Beside that, it makes your job very easy to do so, to extend your Kubernetes environment. I have posted the project link here where you can find it on GitHub, and also what the recommended reads are, where you find the book if you want to learn more about it. And if you have any specific questions to that, you can reach to Alex, and by times allows, he is going probably to answer your questions. So anything about that, Alex, from your side? Would you like to mention something important in that topic?
Oh, well, just that KubeBuilder makes it very easy, as you already said, to easily set up a new operator with some CRDs and even validation and like default variables for the CRDs, which, as I said last time in the meeting, it's great to have such an easy to use tool to get something like that bootstrapped quickly. So just, well, yeah, okay. Just that.
Perfect. Sounds good. Sounds like someone needs also can see the recording. I'm not sure for now if our recordings are on YouTube, but maybe we need to check one day to make sure that our recordings are being uploaded, so that someone that is interested can also listen just to the talk that you had given last time. So let's then continue with the operating system security. And when we talk about operating system security, we talk about many different tools that you can use, or many different systems or subsystems of the operating system layer. One of them is, for example, the mandatory access control, where with respect, you can use, there are two different tools that are well known out there, which is one is the SELinux, and the other one is AppArmor. They would harden your operating system, and that would make it more secure in a sense when it comes to access control, so that you don't rely on providing the access, or that the users themselves can forward their access or the access to their data or files to someone else, but this access is somehow centrally organized, and someone has written the policies, what should be allowed and what shouldn't be allowed. And as I said, there are these two tools. These two tools have some differences within. So SELinux is more having a system-wide perspective, while AppArmor is having more a kind of program perspective. So it tries to actually secure a program with respect to mandatory access control, while the SELinux try to cover all the operating system layer. Another one is capabilities, where you can use the capsh tool actually to make use of the capabilities, to assign or to revoke capabilities to certain programs. And why are capabilities actually important is that before having the capabilities, you could have like two kind of states. So you would have either you run a program as privileged or you run a program as unprivileged. So either all or nothing, like the way. So with the introduction of capabilities, you would have the possibility to provide the program, let's say, a specific set of, as the word said, capabilities. So it needs to do some specific system calls or specific, let's say, administrator capabilities, or you can somehow prevent them from doing that. Like you can, let's say, in a sense, you can close the surface attack. So you wouldn't allow a program to run fully privileged if it's not necessary at all. And this is where this tool is actually very useful, and it has been introduced since many time now in Linux. I don't have the exact date, but yeah, you can read this in the main page for sure. Another tool here is system calls, where you can use, for example, the seccomp or the seccomp BPF tools to use the system calls and to, let's say, prevent or reduce the system calls that a program is allowed to do. Well, with the system calls in general is something that, well, when a user programs tries to do something, like, for example, talking to the hardware, but it's not allowed to do so because it's running on user space. So it talks to the kernel, and it talks to it by executing a system call or calling a system call, so that the kernel can take over, do the job for the process, for the user space process, and get back when that task is done. Get back again where the call have started, so then the program can continue. So this is also very a useful tool. Well, another one, firewalling, sure. Well, accessing your system from outside, or your system going outside of it and calling sites, or being able to browse the internet, the overall internet, and so on and so forth. So you can block the access to specific services and so on and so forth. So this is just for the sake of having something in the list. And the next one that I would like to go a little bit more into details is runtime security, which we'll talk in the next slides. And of course, etc. So you can have you have even more other security tools in in the level of the operating system here, which I left out. Like, for example, secure booting is also a kind of tool or method option that allows you to secure your operating system, or the layer below Kubernetes, as we would like to call in here. Alex, maybe you do want to add anything here, or?
Well, just that in the end, it's not just one tool that will, help you establish security, but in the end, it's the right mix of the tools that you're using there.
Yeah, exactly.
Well,
good point.
Yeah.
Very good point. Yeah, so exactly. This is exactly as Alex put it. You have these different tools exist because they address different challenges and different issues, and exactly the combination of them and why and how to use them in the right way, it helps you make your infrastructure or the layer below Kubernetes more secure. Well, talking to runtime security, so I just have here is just for the sake of showing. So we have on the one side the normal stack, where you have, the function call arguments when you have the return pointer, so the return address of the function that is being executed. So you have the local variables as buffers, and on the right side, you have a kind of called smashed stack where something has gone wrong, a kind of buffer overflow, let's assume has been exploited, so that the return address of the program that has been executed has been compromised, and so it has been overwritten. And so we see that now the new pointer is not showing anymore, or is not getting back to the where the program has been started, but is executing a different program, another machine code. To avoid such things, there have been a kind of tools or let's say methods, or a systematic way on how you can try to prevent such things. And one of them is, for example, the stack canary. So the stack canary is a kind of technique, and it allows you to determine whether this return address has been compromised and it has been overwritten, as we see on the right stack, where we are overwriting the return address, so pointing to somewhere else. So, and in these techniques, the stack canary, it's nothing else, just a random integer which is put in front of the return address just when the program starts. Well, it is, let's say, it might be an offset or two offsets away. So this depends on how the implementation. So this is kind of where the different implementations differ there. So the various implementation differ, but this is the idea about it. And let's assume, so we have an attacker exploiting a buffer overflow, and this would need also to trample or to override the canary. So if the canary has been overwritten, the program will fail. So it would not allow an attacker in order to execute the program, to continue executing its code, because when the program returns, it checks first whether the canary is still the same or it has been overwritten. And if it is overwritten, it fails. And if it is not overwritten, it continues. But as you can imagine, well, this is not very difficult to exploit, because you would be able to find out the offset where the canary is actually set up, where this value is, and you then would prepare your code, your exploit code, so that you are not overwriting the canary. So you can brute force the canary and find out what is the real value, and then include this into the code that you are injecting while you are exploiting this buffer overflow. And so you would be able still, so this doesn't actually help so much. It prevents, well, kind of script kiddies, but an attacker that is skilled, that is knowing what he's doing, that or she is doing, that it's not going to be the way you can prevent that. Another technique is the so-called shadow stack. So this is again another technique in order to secure the runtime, where the return address of a program is protected by having, as well the word said, a kind of shadow stack. So you keep a copy of the function's return address in a secondary separate shadow stack, and where the application accesses that shadow stack in order to identify whether the return address, it has been overwritten or not. It isn't very much, let's say, different from what we said about the stack canary, but well, the difference is here that this value that we are comparing, whether something has gone wrong or not, it's not held in the same stack of the program, but it's held in another stack. So that you can imagine also here, one of the things is that, well, an attacker would try to find out the offset of where is the shadow stack, where is it lying in memory. So at the moment where the attacker can find this, where the shadow stack is lying in memory, it can modify that. So it can identify what is the address that it needs to input into the injection or into injected code, and that therefore it can circumvent that. Another, well, let's say, disadvantage or something that this technique cannot prevent is, for example, it cannot identify if something has gone wrong with the local variables, like if any local variables have been compromised into the stack. Another technique that we know, it's the so-called non-executable stack, or well, as it is called in the Windows environment, data execution prevention. This is actually a hardware feature, which it allows the operating system to mark the data area on the call of the stack as non-executable. So meaning that well, you are now injecting that code into some area of the stack, as we see here on the right stack. So we have an executable here command where we want to open program the shell. But as this area of the stack is, let's say, assigned or is being said that is not executable, you will not be able to execute that command. So you will not be able actually to execute your injected code and to run the program that you are trying to run, like, for example, getting a shell with root privileges. So this solution, it prevents actually the injected code in the call stack from being executed. But also in this, with these techniques, there are, let's say, kind of attacks that can circumvent these techniques. And one of these attacks are the so-called return-oriented programming. So this technique, it suffers against such attacks. And very well, broadly summarized, return to oriented programming, it doesn't inject code, but it builds the code by finding instructions into the executed into the stack, and then it calls, or it creates kind of gadgets. So it finds assembly sequences that can be used for building an injection or the code for injecting, and then it uses them as they are anyway in the stack and they can be used. It uses them to circumvent this kind of technique. So, and one of the last one is the address space layout randomization, which is a kind of answer against this gadget building the return-oriented programming, where is an approach, and it is built in the Linux kernel, also in the bootloader, and it randomizes the location of memory for the stack, the heap, shared libraries. But the effectiveness, of course, of this is that the address space layout remains unknown to an attacker. So all of these addresses are being randomized, so they are not in the default address. So let's say library XY, it's always in an operating system where the ASLR it's not enabled, it would start at some specific default address. And this is, of course, known by attackers, especially if we are talking about open source, and if the attackers have access to the source, they can find out actually what is going to be the default address. And this is what actually the SLR is doing, is randomizing where the default address is by putting an offset. And this offset is actually decided when the program is executed. So not the program, I'm sorry, when the operating system starts. So there is an offset that is being decided, the random offset. And when the system reboots, a new offset is actually being used. But nevertheless, this when this offset is going to be found, so if an attacker is able to find the offset because he is able to identify one of the libraries, and from that it can derive actually what was the default offset of the library and where is now in the memory. So it can actually reverse engineer the offset that has been used by the operating system in the booting time, in the boot time. So it can still try to circumvent that. So, and there is where, let's say, polymorphing as a technique has an answer to all this, or tried actually to mitigate all the disadvantages that we have seen so far. So we see that all of these techniques have advantages and disadvantages, and all of these techniques would increase the effort of an attacker. So it's always recommended to use all of these techniques, so to layer them rather than to not use them, rather than to say, well, I'm not using this because an attack, it exists. So this is not the way that actually you should think about it, but you should think about it, all these techniques somehow prevent a kind of attacks or a kind of attacker, depending on the skills of the attacker. But polymorphing, then it tries to actually address all of these issues that we talked before, and it mitigates this kind of memory attacks, as we talked before, and the runtime. So we have here on the left side, which is very simply explained in the figure. So we have the source code and the dependent libraries, and those are actually scrambled in a sense while they're being compiled. So in the compilation time, two things happens. One is that the library's original assembly instruction set are being logically changed or are being replaced with a logically equivalent one. And the second one is what we have known from the address space layout randomization. There the randomized, so it randomizes the start address for every library and every function within the library that has been scrambled. So by combining both of these techniques, you would be able actually to address all of the issues that we have identified and we have introduced before. So you would be able actually to have a unique copy of your operating system, which would allow, or which would prevent, actually, best to say, would prevent an attacker that it has found an exploit and it has written an exploit code for that vulnerability, and it tries to run this against your system. This is not going to work out if the attacker is using the same code on the system, because this would make your operating system unique, and it's not going to be the same as, let's say, the general or the one that you can download from any repository and then install it on your system. So it would have all actually the disadvantages that we were talking before. But if you have a unique copy of it, it would allow you or it would prevent an attacker to scale. So this is why polymorphing actually it adds on that on the security, and it improves the security in that sense significantly. Nevertheless, also with polymorphing, you can use Polyverse, which is a tool that is implementing that for Linux operating systems. But it's also important to understand, because as we have seen, all of these techniques have been, let's say, implemented or have been brought out there and have been thought and from people while deriving. So we have an issue and we find a way how to address this issue. Nevertheless, I mean, this is a kind of race. So then people trying to exploit that or to circumvent that method will always ask the question, so how can we do that? And also with, this is not different with polymorphing well, the tools that are implementing it. And I think there are two things that are worth investigating or thinking about it, how easy it is to circumvent the technique. And one of it is the assembly instruction set substitution. So we said it does one thing, so it substitutes the assembly instructions. So the questions that are here, in order to understand how easy it is to circumvent that, is what is actually the space of equivalent instruction set for a given library, function, or instruction? So how many different assembly instruction sets can you create so that it's still logically equivalent to the previous one? Well, assuming that the set is known and countable, so that it's not like you need more than the universe has existed so far time for exploring that set, can this set, or which of this set can be misused for mounting attacks? For example, as we said before, like mounting a return-oriented programming attack while you find the gadget or the instruction set that you can use for creating your injection code. Another question is start address randomization. So this is, let's say, a kind of idea borrowed from the address space layout randomization. And the question is here, how it does it differ into the implementation? So because Polyverse itself, it's not the one implementing this technique, it's not open source, it's of course interesting to know where it differs from there. And assuming, for example, that it differs such that, well, the different offsets are used, does this really increase the effort significantly? So because the same way, the same techniques I can use to identify the offset in the ASLL, the same way I can also use when polymorphing is done. But the question is here, what is the set? So how much time or effort I am being put on to do that? Yeah, so that's it actually. So we are already in the questions. Maybe Alex want to add anything, or from his side, any comments or any ideas, any suggestions, and let's see if there are any questions afterwards.
It's just interesting to see the different levels one can use to well, mitigate attacks, or to, well, try to prevent attacks to a certain extent. No.
Cool. Yeah, so you can do many things and different things, and it's interesting how people always come with an idea how to circumvent these ideas. It's this is the amazing thing, to be honest. So, well, let's see if there are any questions out there. So far, so then, well, if there are questions, feel free to reach us out. Alex and myself, even though we are, of course, working on projects and so on and so forth, but we'd like also to learn from you and to get challenging questions that put us in a position where we think further and try to find out solutions that maybe we didn't think before. So feel free to reach us out. Thank you, Alex.
Thanks for you to you as well.
And, well, see you then next time.
See you.
Bye.
Bye.
Bye.